The giant isopod. Flip over a rock in your garden and you'll find a gray bug barely bigger than a fingernail. Now picture that exact body plan scaled up to the size of a house cat, sitting motionless on the seafloor, having gone years without touching a single meal. That's not a thought experiment. Bathynomus giganteus is a genuine relative of the pill bug you just imagined, except this version reaches roughly 50 centimeters and several pounds, while its garden-dwelling cousin rarely tops 2 centimeters. Somewhere between the shallows and the seafloor, the same basic body plan got stretched to an extreme nobody would predict from the miniature version. One leading explanation involves oxygen. Cold water holds more of it dissolved than warm water, letting cold-adapted bodies grow larger without their cells running short of air. Food scarcity plays a role too. On the abyssal plain, meals arrive unpredictably, sometimes as a whale carcass drifting down from far above, so a bigger body stores more reserve fat for the stretches of nothing in between. One captive isopod reportedly survived 5 years without a single meal, coasting on stored energy alone. When food finally does appear, it gorges until its armored plates visibly bulge outward. Its oversized compound eyes, built from thousands of tiny lenses, catch whatever faint light drifts down from the surface far above. This is not a monster. It's a woodlouse that never got the memo about staying small. The giant grenadier. There's a fish alive right now on the cold slopes of the North Pacific that was already fully grown before some of the people reading this were born, and it still might not be finished. Albatrossia pectoralis stretches past 2 meters, tapering from a blunt head into a thin, rat-like tail, patrolling depths between roughly 100 and 3,500 meters down. Otolith studies, which read growth rings inside ear bones the way foresters read tree trunks, suggest some individuals reach 50 years or more, with females not even reaching reproductive maturity until their early 20s. That slow clock matches a pattern researchers keep finding among cold, deep-dwelling fish. Metabolism drops with temperature, growth stretches out, and lifespan extends to match. Larger bodies also burn energy more efficiently per unit of mass, a relationship known as Kleiber's law, meaning less food gets wasted keeping one large grenadier running compared to several smaller fish doing identical work. Its oversized eyes and elongated sensory canal pick up faint vibrations and scraps of light in water where sunlight has never once penetrated. Trawl surveys off Alaska and Japan now haul up enormous numbers of this fish as incidental bycatch, animals that spent decades quietly aging in near-total blackness before ever meeting a net. Longevity here isn't a bonus feature. It's the entire survival strategy. The black swallower. A fish smaller than a dinner plate is about to make a decision that could kill it: swallow something twice its own length, or go hungry. Chiasmodon niger measures barely 25 centimeters, yet it routinely seizes and swallows prey more than double its own length and roughly 10 times its own weight, a stomach feat with no real equivalent among shallow water fish. Its upper jaw hinges loosely at the skull instead of locking rigidly in place, letting the mouth swing downward and engulf a body wider than its own head. Backward curving teeth fold inward to admit the meal, then lock outward to seal the exit shut. The real trick sits behind the jaw, a stomach lining stretchy enough to balloon around prey many times its resting size. In a habitat where the next meal might not arrive for weeks, this all-or-nothing gulp makes ecological sense. Better to overreach once than starve waiting for something smaller and safer. The gamble occasionally backfires spectacularly. Specimens have turned up floating dead at the surface, their swallowed meal too large to digest before decomposition gases built inside the distended belly and dragged the swallower upward against its will. Most known specimens, in fact, were recovered exactly this way, not hunted, not caught, just undone by their own ambition. The giant devil ray. For over 200 years, an entire species swam around wearing a name it never earned. Mobula mobular picked up the title giant devil ray after fishermen and early naturalists repeatedly mistook stray oceanic manta rays, genuinely massive animals wandering into the Mediterranean, for this smaller, spine-tailed species native to the region. Once taxonomists finally untangled the confusion, they found Mobula mobular tops out around 3.5 meters across, respectable for a ray but far from giant within its own family. The oceanic manta it kept getting confused with can stretch past 7 meters. Researchers have since proposed renaming it the spine-tailed devil ray, a title that at least describes something the animal genuinely has, since it remains the only mobulid carrying a spine on its tail. What it lacks in true scale it makes up for in filtering efficiency, funneling plankton and small schooling fish through gill plates using curled cephalic fins that give it the horned, devilish look responsible for its common name. It favors open Mediterranean and nearby Atlantic waters, diving deep after krill while rarely lingering near the surface long enough for easy study. Nobody set out to deceive anyone. A simple case of mistaken identity just quietly became permanent zoology. The giant squidworm. A creature with 10 tentacles trailing from its head sounds like something a submarine crew would hallucinate after too many hours in the dark. It's real, and it's barely the size of your hand. Tuthadodrila sami stretches roughly 9 centimeters, hardly gigantic by any ordinary standard, yet it earned its dramatic nickname purely from silhouette. 10 long, trailing appendages fan outward from its head like tentacles, making a small segmented worm resemble a hybrid of squid and earthworm drifting through open water. Discovered in 2007 by a remotely operated vehicle exploring the Celebes Sea near the Philippines, it swims roughly 2,000 meters down, just above the seafloor, in a zone few cameras had ever properly surveyed before that expedition. Instead of eyes, it relies on paired chemosensory pits to detect subtle shifts in water chemistry, tracking marine snow, the slow drift of organic debris falling from above, which forms the bulk of its diet. Its discovery mattered less for the animal's dimensions and more for what it revealed: an entirely new genus living in open water just above the mud, overlooked for as long as humans had been exploring these depths. Sometimes the biggest find in the ocean isn't the biggest animal at all, just the biggest gap in what scientists assumed they already understood. The Atlantic wolffish. It looks like an eel that lost a fight with a wolf, and its mouth is the reason nothing wants a rematch. Nothing about its modest 1.5-meter frame suggests anything giant, until it opens its jaw. Anarica's lupus carries rows of blunt, fong-like teeth up front and flattened crushing molars behind them, an arsenal built entirely for cracking sea urchins, whelks and thick-shelled clams that most predators avoid entirely. Those molars wear down constantly under the strain, so replacement teeth migrate forward from the back of the jaw throughout the fish's lifetime, keeping the crushing surface sharp for decades. Its blood carries antifreeze glycoproteins that prevent ice crystals from forming internally, letting it patrol rocky ledges in water hovering near freezing, conditions that would stiffen most other fish into torpor. Unusually for anything with fins, the male coils around the egg mass for up to 4 months without eating, guarding it from predators until the young finally hatch. None of this involves size in the way we usually mean giant. The giant here is entirely mechanical, hidden inside a jaw engineered to outcrush shell defenses that took millions of years to evolve. Fishermen once nicknamed it devilfish purely for its snarling face, never suspecting the real story was happening several rows further back, inside its throat. The giant larvation. Imagine an animal smaller than your thumb building itself a house wider than a dinner table, then throwing it away and starting over the very next day. Even its own discoverers admit the name oversells the animal and undersells its architecture. Bathocordeus itself measures only 3 to 10 centimeters, tadpole-shaped and nearly transparent, giant purely in comparison to relatives barely reaching a few millimeters. What it builds, though, earns the title outright: a balloon-like mucus structure called a house that can exceed a meter across, dwarfing the tiny body pumping away somewhere inside it. 2 nested filters strain seawater as the larvation beats its tail, an outer layer blocking anything too large to eat and an inner layer funneling edible particles toward its mouth. Researchers using a specialized underwater laser system have measured filtration rates faster than any other zooplankton on record, quick enough to filter an entire bay's worth of water within roughly 2 weeks. When a house clogs with debris, often within a single day, the larvation simply abandons it and secretes another from scratch. Discarded houses sink toward the seafloor loaded with trapped carbon, making this fragile, barely visible creature a meaningful player in how the planet buries atmospheric carbon in the deep ocean. The animal itself stayed tiny. It just built something enormous to survive inside. The megamouth shark. A Navy crew testing sea anchors off Hawaii hauled up something that shouldn't have existed, and the shark world hasn't fully recovered since. On November 15, 1976, a U.S. Navy vessel off Oahu pulled from the water a dark, blubbery shark over 5 meters long with a soft, cavernous mouth unlike anything described in existing shark literature. Megachasma pelagios took researchers 7 years to formally classify, and its discovery forced the creation of an entirely new shark family, the first such addition to the field in over half a century. Growing past 7 meters, it swims slowly, often under 2 kilometers an hour, sweeping its enormous rubbery mouth through deep water to filter copepods and krill using roughly 50 rows of small hooked teeth built for straining rather than biting. For decades, its pale mouth lining was assumed to glow, luring prey through bioluminescence, until histological studies found no light-producing organs there at all. The shine likely comes from denticles reflecting light generated by the glowing plankton it feeds on, not light of its own making. Fewer than 200 confirmed sightings exist across nearly 50 years of searching. A shark large enough to be mistaken for a sea monster, and still one of the rarest large animals most marine biologists will ever see alive. 8 animals, 8 completely different reasons for their size, or in several cases, for a name that promised size and delivered something stranger instead. That's usually how the deep ocean works. It rarely builds what you expect. It builds what survives.